All right, welcome back, everyone. We're going to continue with the second lecture of Anne-Marie, please.
Okay, so thank you. So today we will more concentrate on temporal representation, but first we will finish some things about some of them, so the square integrable mode center. And first we will introduce the notion of unitary representation. So representation is would be said unitarizable if there exists a G invariant positive definite Hermitian inner product on the vector space of a representation. And after completing that vector space with respect to the given inner product, we will get a unitary representation of G in an Hilbert space. So discrete series are special cases of unitary representations. And as we have already seen, they split into two classes, supercuspidal representations, which, as I already said, are irreducible unitary representation whose matrix coefficients are compactly supported at the center of a group, and representations which are usually called generalized spatial representations, which are the irreducible unitary representation whose matrix coefficients are square integrable mod the center, and which are not supercuspidal, which means that they are sub-representation of a representation properly induced by a parabolic subgroup of G. And we have already seen an example of a discrete series of such discrete series as the Steinberg representation. So now, when we have a square integrable modulo center representation, you can irreducible one. We can compute. We can attach to it its formal degree, which is the unique positive real, such that when you consider the following, we integrate on G mod its center of the product of the following coefficient, then matrix coefficient, you get the product of element in the vector space up to some terms, which is the inverse of a formal degree. But the definition depends, of course, on a choice of a R measure on Z mod its center. We will have we'll need a slight generalization of square integrable mode center representation, which are called essentially square integrable ones, which are obtained by just twisting the square integrable mode center representation by some quasi-character of a group. And in that case, we define the formal degree of that representation as a formal degree of a original square integrable representation. Also, in computing the formal degrees, it's easy to do it when the representation is induced from an open, irreducibly induced from an open mode center subgroup of G. And in that case, the formal degree is just the degree of induced representation divided by the measure of a volume of the subgroup divided by the center of the group. So, so this would be useful in applications. Now we have a list of a representation of SL2. So first, the center of SL2F is just 1 and order 2, the identity and minus the identity. And so in particular, it's followed by discrete series of SL2F consist of those irreducible unitary representation whose matrix coefficient lies in L2 of SL2. So we'll have now, if you take a character now of a torus. We have already seen that the torus in maximal torus in SL2 is just is isomorphic with the F cross, and you induce parabolically induce such a character, then the induced representation is reducible if and only if the character chi is a quadratic character of F. But it is not trivial, and it has order 2, and which means if you that character is one of the three characters that we have defined before sign A, where A is epsilon F of the uniformizer of a product of both. And when the representation, the induced representation is reducible, it is a direct sum of two irreducible components, and we will denote this two component as, so if you denote the induced representation as pi sub chi, we'll denote its two irreducible component as pi chi plus and pi chi minus. So now we can classify the irreducible unitary representation of SL2F. So it's a unitary dual. So I am assuming for simplicity that P is not equal to 2, because if P is 2, we have more supercuspidal representation. So we have a unitary principal series, the one for which pi chi is irreducible, and so chi is not equal to 2. And pi sub chi is equivalent to pi chi minus 1. We have the two irreducible component of a principal series, pi chi, when chi is a quadratic character, the supercuspidal discrete series that we have already talked about it yesterday. And then we have what is called the complementary series. So it is the parabolically induced representation from a character chi sub s, where s is in the interval, the open interval 0, 1, and chi s is defined as the p-adic chi s of G is the p-adic absolute value of G at the power s. And then we still have two other representations that actually we have already seen, which has used to say that they occur at the end of a complementary series, because it's similar as before, but when s is equal to 1. And in that case, so for the character, so chi1, which is just the norm, we get the trivial representation and the Steinberg representation, which is square integrable. So now I would like to explain a useful characterization of discrete series in general. So we would take, and it will involve a notion of central exponent. So P will be a parabolic subgroup of our p-adic group G, and pi v an admissible representation of G, chi a smooth character of a split component of L, denoted AL. So just recall that it is the F point of a maximal F split torus, which is in the center of L. And we also fix K sub L, an open compact subgroup of a Levy L. And then we define the following space, which is the characteristic space. So you take the set of elements in, so you take your representation pi v, you consider its parabolic restriction, R, G, L, P of V, and then you consider, you take the fixed point of this restriction by the group K sub L. And then the set we are interested in is the set of that in KL fixed vector, such that there exists an integer a positive integer g. That's why if you can compute your RL pi of t minus chi of t identity at power g, this when you apply this to the vector v, you get 0 for any element t in AL. So it's clearly the usual notion, I mean, a generalization of a usual notion of characteristic spaces for matrices. And then if you consider, we can see that we can check that when you consider the fixed point of the parabolic restriction of V under that subgroup KL, you get a direct sum over the set of smooth character of A of these characteristic spaces. So this will be useful for us in order to introduce the notion of exponent. So what we will do now. First, we observe that if we take another open compact subgroup of G, KL prime, which is contained in KL, then of course, if you take the invariant by KL prime, they are bigger than the invariant by KL, and it's the same for the characteristic space. And you will denote by RGLPV sub chi. Okay, I'm sorry for the union of all the KL of this invariant spaces. Now, if this if we have RLPV sub chi, which is non-zero, then we say that chi is an exponent of pi for p. And the set of exponents will be denoted by XALRLP. And now we can introduce the following notation. We fix a minimal parabolic subgroup pi 0 such that, and you consider I was okay. Sorry, I was just trying to stop the noise. So we fix a parabolic subgroup, minimal one, pi 0 included in P, and then the split component of L is contained in the split component of Levy of pi sub 0, and then you denote by L by X star of AL, the group of rational character of AL, and you can define consider the tensor product over Z of this group with R, and similarly for the dual space. And then using this, you can define, if you denote by sigma A0, the set of root of A0 in G, and sigma subhead of A0, the subset of reduced root, then you can consider denote by delta 0 the set of simple root in the subset of reduced root, and by delta of P the restriction to AL of the root which are simple root which do not belong to the similar to the similar set of simple root in the Levy. Okay, just kind of classical notation, but this is useful in order to have the following characterization of square integrable representation mode the center, which is the Castleman criterion. If for any parabolic subgroup P, and any exponent chi, when the real part of the exponent is in the positive chamber, which is defined like this. So you take the sum of all the linear combination with positive coefficient of the root which are in delta p. So now, of course, when we have such a statement, you could be interested to look to see what it is when you replace the condition being positive, but the kind of the condition that being just non-negative, and it is exactly what we get. So, and doing that, so you define, get the notion of temper representation. So it's a representation which is admissible, and such that for any parabolic subloop P and any exponent chi, we have the real part of chi, which is in the closure of a previous set. And it's also, if you consider just a irreducible unitary representation, then it is it means the following characterization. So it is tempered if and only if its matrix coefficient lies in L2 plus epsilon of G mod Z for all epsilon strictly greater than 0. So of my definition, temporal representation are purely generalization of square integrable mode center representations. And so I will denote by ER square, two for the square integrable mode center representation and ER-T for the temporal ones. And a result of Alexandra is the following theorem, that any irreducible temporal representation of G occurs as an irreducible component of a parabolically induced representation from attached to a parabolic subgroup P and a square integrable mode center representation of that the levy of P. And also the G conjugacy class of this pair M omega is uniquely determined, and it's usually called the discrete support of a representation pi. So last time we have considered parabolically induced representation from irreducible supercuspidal of a Levy subgroup, and today we are replacing this notion by, in the case of temporal representation, by a discrete series representation in the discrete series of a Levy. So we'll denote by omega of G the set of pairs of G conjugacy classes of pairs L sigma, where L is a levy of G and sigma is irreducible supercuspidal representation of L, and by omega T of G, the similar set, but in which I take the representation to omega to be in the discrete series of M. And by this theorem and the previous Alexandra theorem from last time, we have two maps. When we start with an, okay, there's something, so the last time it was for any irreducible smooth representation, and today we are just considering the one which are unitary. And so we have two maps. So we went one which attached to an irreducible representation, a pair in omega of G, and one which is attached to it, a pair in omega T of G. And there is a nice relation between those maps, nu and nu T, which can be written as the following compatibility. So saying that this diagram is commutative. So we have already this map, nu and nu T, and the map, so omega G is so is a set of supercuspidal in N, and you take, here you have representation. So if you take a supercuspidal which is unitary, it is already discrete series. But when you take a representation which is an inverse discrete series of M, it is not necessarily supercuspidal, and so we can apply to it the map the map nu, but in M, and you get, this is the map that I did not here, Z, which attached to M omega, it's supercuspidal support. And this diagram is, this triangle is commutative. In the special case where the group G is GLN over F, then first the map Z is injective, and the map nu T is bijective, for the reason that any unitary, when you take an irreducible representation of a Levy, and sorry, square integrable mode center, and you induce, then you get an irreducible representation. Okay, so we will come later. I mean, this relation will show up again later. And now, in the same case, in the same feature as for real groups or curves. So we have seen in picture lecture that we have a notion of a Plancherel formula, and in particular that the tempered, irreducible tempered representation of G, which is called the set, the tempered dual, is the domain of a Plancherel formula. So we have the same result here. In order to state it, I'll need to introduce some more notation. So first, I will denote by curly P the set of pairs formed by parabolic subgroup. So now my parabolic subgroup, I will denote them by Mn, where M is a Levy and N is the unipotent radical, and O, where O is, okay, I don't know if I did not, okay, I did not, okay, sorry, I did not explain what is O. It will be explained later. So O is the orbit of a discrete series representation of M by the group under the action of a group of unitary characters of M. And to such pair, QO and Q prime O prime will be said to be associated if there exists an element in the Y group of G which sends the Levy M to the Levy M prime and the orbit O to the orbit O prime. And you will fix and denote by P tilde a set of representative for these classes of association. And you will also need the following group. So that will be denoted by WMO. So you take the element in the normalizer of M, which fix the orbit O mod M. And we also need the following notation. So when you take a function locally constant and compact support function f on G, then you define the function f check as just by f of G is f of G minus 1 for any element in G. And finally, I recall the notation from yesterday about when we start with a representation, smooth representation of G and a function f, then you define the operator pi f from V to V as the following integration. So now we have all the notation to state the Plancherel formula. So the main reference for it is the paper by Valspurger at the Journal of IMG in 2003. And the statement is the following. So you start with a function f in CC infinite of G and an element G of G, and you can express the value of your function f at the element G as the following sum. So it's a sum over all the association, over all Q, the pair QO in this association set, representative element of the association set, P tilde, some constant, but I just call it CGM, which depend on G and M, which it's possible to make it more precise, but we not need it today. And the inverse of the order of the previous group WMO. And then you consider the integration over the orbit O of three terms. So the first term is mu GM of omega, which is where mu is the Plancherel measure, which defined by Harishchandra. I will not give the definition today, but I will. Okay. And the second term is what we have just viewed at the beginning of the talk. It's the formal degree of omega. And the last term is the trace of the operator pi f, where f is the parabolically induced representation from m of omega. And recall that omega is in the discrete series of n. And lambda g is just translation, left translation. So this formula is essentially the same application as for real groups. So it's an important result. And okay, it also has an interpretation at the level of C-star algebra, but I hope I will be able to explain this tomorrow. For now, okay, here comes the notation of the orbit, which is not in the right place. So omega is just what I said. You consider the twist of a given, of a fixed representation omega by all the unitary unramified character of our Levy M. And what is an unramified character? So it is a character which is trivial on every compact subgroup. And so we will denote by X of M the abelian group of unramified character of M, and by X sub U of M the subgroup of XM of the unitary unramified characters. So now I will just go back to the definition of this map. So we have this map. So we start with an irreducible temporal representation up to equivalence, and you send it by this map mu t to its discrete support. So now we can consider the fiber of this map mu t, and it's what it is stated here. So we start with so we have a Levy M, we have O, an orbit of a discrete series by unramified unitary character. And first we denote and we denote by theta the G conjugate class of this pair. Or if you want to specialize to specialize a base point, you will write it as M omega G with bracket. And you will denote by B, flag B square of G, the set of such pairs. And such a pair would be called an inertial discrete pair in G. And so now when you start with a parabolic subgroup Q of G with Levy M, you will denote by here T is for tempered, here T theta of G, the set of irreducible representation of G that occurs in one of the parabolically induced representation and PG of omega tensor by chi. So sometimes when I really want to precise the Levy, I wrote it as I NP of G. And yeah, I just write it like this, but it's the same object. So omega is a square integrable mode center representation of M, and chi is a unitary harmonified character of M. And so the fiber of theta of the map under the map nu T is what we denoted as ir T theta of G. And the interest of this notion is that we get the following decomposition of a tempered dual of G, which is due to Roger Plyman, is that you can write the tempered dual of G as a disjunct union on the theta inertial discrete pairs of this set just defined above, so RT theta of G. And what would be the goal? The goal is to describe the structure of this component up to strong Morita equivalence. So in as far as I know, in general, it's not known, but we have a result in several cases. But before that, I would like to relate this with C-star algebra. So we fixed a left, we now fix a left invariant R measure on R group G and consider the Hilbert space L2 of G. Then the left regular representation lambda is of L1 of G is defined by the convolution product. And the reduced C-star algebra of our periodic group G, here denoted as C-star R of G, is the C-star algebra generated by the image of lambda. And it's a very interesting object, and in particular, its spectrum can be identified with the tempered dual of R group G. And this is the way to understand this decomposition. So this will be done using in relation with this C-star algebra due to the following decomposition. So the C-star algebra, reduced C-star algebra of G admits a decomposition as a direct sum of subalgebra which would be denoted as C-star R G theta, where that subalgebra has a spectrum exactly here T theta of G. So you will define this subalgebra, but it would take, I would do now, but for that we need to introduce our object. So we start with omega, a square integrable mode center representation of R Levy M, and you assume that we have fixed an R measure on G, and also fix a maximal compact subgroup K of G with measure of total mass 1. And we may and will assume that K is a good special maximal compact in good position. So I will not explain what it is, but the important point is that we can write our periodic group G as the product of K with P. And P is our parabolic subgroup of Levy M. Okay, sorry, it should be Q because now I decided that parabolic is called Q. But anyway, okay, sorry for the confusion of notation. So, so now my parabolic will be denoted by P. So we denoted by EP of tau, when tau V is a representation in the orbit O as the space of function. So V tau is the space of a representation tau as function from G to V sub tau, but are right invariant under some compact open subgroup of G and satisfy the following relation. So here delta P is the module function from the parabolic subgroup. And you will denote by IP of tau the representation of G on this space which acts by left translation. Then we can consider the compact picture. So we would take similar space, but here the function of from G to v tau instead of, from K to v tau instead of G. So and we assume that they are right invariant under some open compact subgroup of K now and satisfy the following relation. So when you compute F at K, M, N, so M is an element in the intersection of a Levy and K, and same for N, for the unipotent radical of a parabolic, then we have this relation between F, K, M, N is equal to tau M minus the inverse of tau M times F of K. And we will need to consider the Hilbert completion of both these spaces with respect to the usual inner product, which is written here. And we still denote by IP of tau the representation of G on this Hilbert space. So now, if we take an unitary unamified character of our Levy N, and we can consider the following linear isomorphism. So we start with a function f in H, the same is HP of omega tensor chi. So with the previous definition where tau is taken to be equal to omega tensor chi, and then you have a map, which is just defined as a restriction map from HP omega tensor chi to HPK. And okay, we denote this map as FKP of chi. And then we can consider the representation of G on the space HPK, which is defined as follows. So you have in the middle, you have just the parabolically induced representation of omega tensor chi, and you consider the conjugate of this by FPK of chi. And then we consider, as usual, the following operator, which is what we have already seen before, but now, as for the Plancherel measure, the Plancherel formula, we take the integration of Fg times the parabolically induced representation of tau, but here we are looking at the compact picture, so which is the representation we are just defined above. And then this operator is compact and depends continuously on tau. And you will also need the following notation. So we denote by K of HPK the algebra of compact operators on this space. Now we have all the ingredient in order to define our subalgebra C star R G theta. So we have a linear map from CC infinity G to the function from O to this space just defined K of HPK, and up completing the space of function on G to the reduced C-star algebra of G, we get a C-star morphism from the C-star algebra of G to this to C of O, K, HPK. And so we have a C-star morphism, and we will define the subalgebra we want as the image of the C-star algebra of G under this morphism. So if you can, and then we get a morphism from the C-star algebra of G. So we can do it for each component theta. So we get a morphism from the reduced C-star algebra of G to the direct sum of these subalgebras over all the theta in our set B square of G. Okay. So, and the result of the Roger is that this map is in fact a C-star isomorphism. So we get a decomposition. So we get the decomposition, expected decomposition. Okay. So now we would like to. Okay, it's already a very nice result, and the point is that in order to understand the C-star algebra of J, you can do it block by block. So it will be enough to understand for each theta the subalgebra C R star G theta. And so it is the objective we have now in mind. And for that, you will need the following object. So you will start with so we will fix theta, and we will attach to theta first a certain extended Y group as follows. So we consider the normalizer of theta. So which is what? Which is the element of the normalizer of our Levy M, such that so we do not ask that any element in the normalizer of M will fix omega, but we will request that the image of omega, the conjugate of omega by n is isomorphic to omega twisted by some unramified unitary character of n. And we consider, of course, the n is contained in that group, and you can consider the quotient group, so ng of theta mod m, that will be denoted by w sub theta, and we call it the inertial stabilizer of omega. And this is the kind of group that we will be interested in. So first remark, as we have already seen yesterday, we have, in the case of real group, we have a similar construction. And in that case, this C-star algebra admits a nice determination up to strong Morita equivalence. So now we will see that an analogous result holds when F is a p-adic field, but under the assumption that the action of that group W theta on O admit a good fixed point. So this is a joint work with Alexandre Avgoustidis. And so we'll come soon to the situation. So the point is that, in fact, we can treat all these cases together and see that for real group, I mean, when I say together, I mean for real and for p-adic groups, but for this assumption is always satisfied in the case of real fields. So in particular, it provides a new a proof of as a Wassermann result for real groups.
Anne-Marie, there is a question.
Yes.
Is it possible to obtain a similar decomposition for the twisted reduced C-star algebra when you twist it by a cocycle, 2 cocycle on G?
Okay, it's an interesting question, but I don't know. But in fact, it's possible. But because what we will see soon is that we also have a cocycle which will arrive now soon. So maybe it's related, but it's
okay, maybe we can revisit. Thank
you. Okay. Okay, so now, until now I have defined the stabilizer of theta But in fact, we will need something finer, which is the stabilizer of the representation, this square integrable mode center representation omega itself. So it is the definition which is here. So denoted by W sub omega. And so the interest of that is that for this group, we have the, as for real groups, we have at our disposal the Knapp-Stein decomposition of this group. So W omega is a semi-direct product of W prime omega with a certain group R omega. So and W prime omega is a Lie group, finite Lie group. So, and it is defined as follows. So for any root attached to a Levy subgroup alpha, which contain M, you consider the set of root for G of M denoted by delta, and then you have a B. So this is so in I should have precise in the Plancherel the description of the Plancherel formula. I have said that there is some function mu that occurs, which is the Arichandra-Plancherel measure. So it was the Arichandra-Plancherel measure for the group G, and here we are considering the same function, but where in the case where G is this group M alpha. And we can consider the set of root alpha and delta, which occurs as 0 of a function mu alpha. So it's what we call delta prime. And this set is itself a root system. And you will denote by W prime omega its Lie group. And the point is that so this W prime omega is a subgroup of W omega and admits a complement, and the complement is the group we denote by R sub omega, and it can be defined as characterized as the element in the big group in W omega which send positive root to positive root. So this is a general feature that we will see again tomorrow in a different situation. And by definition, because W omega is fixing, I mean, it's we conjugate it's the element in the normalizer of M such that N omega is isomorphic with omega. In particular, it is N omega is isomorphic with a twisted of omega by an unramified character, just take the trivial one. So it's clear that W omega is contained in W theta. And so this definition also valid for real groups. And when F is real, the action of W theta has always a fixed point. That is, there always exists an element in the orbit, omega, such that in fact W omega is equal to W theta. For PID groups, we do not know, but at the moment we do not have a counterexample. But if the group G is a quasi-split symplectic, so it's a classical group, so it's a quasi-split symplectic orthogonal or unitary group over F, then for every theta, the action of W theta has a fixed point. So we will now take this as an assumption, and you will denote the fixed point by omega, small omega. But this is not enough, so we will need some other property of our point omega. So we make the following definition. We say that omega is good if for every point in the orbit, so we can set a point tau. So tau is the orbit of omega under the unitary unramified character of M. So by Knappstein decomposition, I named the decomposition I have just recalled above. So we can consider this decomposition for the group W sub tau, but also for W omega. And we request compatibility in the following sense. So first, we ask that omega has the bigger Y group part, so which means that W prime tau is contained in W prime omega, and also that the R group, so the group R is called the R group, so the R group R sub tau is isomorphic with a subgroup of R omega. So this condition are satisfied in it's possible to find good fixed point in many situations, but it's also but not always. So we'll see tomorrow example of bad fixed point. But in the for today, I would like to recall some result of about intertwining operators due to Vaz-Piaget, Langlands, and Arthur, that will be useful for us. And one result is, so first is the definition of the intertwining operators. So we start with an element W in W theta and a unitary character, unramified character of the Levy. And there is an operator in the compact picture that intertwines these two induced representation and satisfied an intertwining relation, I would say, but up to some cocycle. So there is a cocycle, eta sigma. So it is a cocycle on W theta cross W theta. So this is a situation which is more complicated than in the case of real groups, Lie groups. And so we have the following result. First, that the map we send R to A of R2 defines a projective representation of the R group on the space HKP. And the multiplier of this projective representation is the restriction to R2 cross R2 of the previous cocycle. Then Arthur constructed the following notion, which is a central extension of the R group. So by considering a central extension of the R group R sigma by a certain central subgroup, and so it's the group that you will have to consider in our situation. So I will maybe give more detail later. And then the interest of this is that we can describe the irreducible component. So, okay, sorry, at some point I changed my notation. So this sigma should be omega, so it's a discrete series representation of a Levy M. And when you induce it, you can look at describe the irreducible parabolically induced sigma. You can describe the irreducible component of this parabolically induced representation. And they are in natural bijection with a set of irreducible representation of this extended R group, R tilde sigma. And moreover, so it's not all the representation, it's the representation of the extension, which have a central character sigma theta, which is given by the inverse of the cocycle. And this extension also comes with a central idempotent, which acts in its group algebra. So it is the minimal, it's a minimal idempotent in the group algebra of Z sigma which such that when you apply P tilde to the group algebra of R tilde sigma, you get the twisted algebra of R sigma by the cocycle. Now, if you assume that the sigma is a good fixed point for the action of W theta on O, then we get a strong Morita equivalence between the C-star algebra CRG theta and the image by P tilde of a group of a cross product algebra of O mod the Y part of the group, so W prime sigma, semi-direct product with R sigma tilde. So how we can interpret this this result, which so we have okay, first we know that strong Morita equivalence preserves spectra. So if we have two representations which are with a strong Morita equivalence between them, then A and B are, if you have two C-star algebra which are strongly Morita equivalent, then they have the spectra, homeomorphic spectra. And the interest is that we get a strong Morita equivalence between the algebra on the left, which is a block in a C-star algebra which is non-commutative, and an algebra on the right, I mean the image under P tilde of an algebra which is almost commutative, because it is the cross product of a commutative C-star algebra by a finite group. Finite group is R sigma tilde. So another thing, when the group, in many situations, for example, for classical groups, we do not need this extension of R tilde, so we do not have P tilde, it's just the identity, and you can replace R sigma tilde by just R sigma. And this allows to infer the topology on the temperature in a way which is related to the reducibility of the induced representations. So I will, okay. So it will be the end of my talk for today. So this is just one. So this is just inside the temperature. So tomorrow I plan to give some more detail on this, and then come back to the smooth dual, and to try to explain how you can view you can describe the smooth dual in a way which is slightly similar to this, and inside of it to see the temperature dual and relate this with explain how this can be related with Baum conjecture.
Thank you very much, Anne-Marie. All right, any questions or comments to the lecture? Is it true? Did I recall from Roger's comment? Maybe it wasn't during the meeting, before the meeting started. For GLN, the R group is trivial. Is that?
Yes, for GLN, the R group is trivial. Yeah. But for SLN, we have a non-trivial R group, but we are cyclic group in many cases.
And your result about this having fixed point for this quasi-split symplectic unitary orthogonal, is it because it's not true anymore beyond those groups, or those are the only groups you were able to prove it for, your result for?
So, sorry, could you repeat your question? So
you resolved with Alexandra about having a fixed point for certain class of groups.
Yes.
It doesn't extend, or the proof doesn't go beyond. So is it untrue for remaining exception different?
So we expect that it is always true.
Okay, I missed that part. Thank you.
But for good point, no. I mean, we have example of bad points, bad fixed point. So the situation is that we expect that it's always a fixed point, but it might be not good.
Mm-hmm. There's a question.
Yes.
Is there a well-known representation that is tempered but not square integrable?
Yes. Okay, I think I gave example in already in SL2 when I gave a list, when we have when we have principal series that are irreducible. This one are tempered but not irreducible. Sorry, induced parabolically induced representation from unitary character of a torus. When we induce representation is irreducible, you get a tempered representation, which is not square integrable. Yeah.
By the way, so the Harishchandra criterion about having compact Cartan also covers p-adic situations, right? Is that true? So, existence of discrete series representations, Harishchandra's characterization also works for p-adic groups, or it's just for real reductive groups, having compact Cartan?
So I think for p-adic group, we always have discrete series.
Always.
Yeah.
Just I mean, an example is just taking this involution. I mean, this direct sum of.
That's very
yesterday of a trivial representation, and then you get one. So in this respect, it's different. It's different from real case.
Any other comments? Another silly question then. Okay, so how about the supercuspal ones? Do they also always are there?
They are what you say?
They are always existing as well for every group?
Yes, they always exist. Yeah, but the proof is more involved. Yeah.
There's a lot of differences, this p-adic situation. All right, then let's thank the speaker again for both speakers of today. Thank you very much, Hang and Andrew. So I'm going to stop the recording. I should have perhaps done it earlier.